Hello, and welcome back to Astronomy News with the Cosmic Companion. This week we're joined by Dr. Meridith Joyce of Australian National University. We'll talk about her work finding that the star Betelgeuse is both closer and smaller than astronomers believed. We're also going to take a look at the Osiris-Rex Spacecraft, which touched down last week on the surface of the asteroid Bennu. We'll examine a new study identifying 1,000 worlds where extraterrestrial astronomers could, theoretically, easily see signs of life on Earth. Also, one exoplanet the size of Neptune, which is found to be orbiting far too close to its parent star. Finally, we're going to take a look at findings from the ALMA network of radio telescopes, revealing the role volcanoes play in forming the atmosphere of Io, one of the largest moons of Jupiter. The Osiris-Rex spacecraft touched the asteroid Bennu on October 20th, collecting samples of material from the rocky body. This touch and go lasted less than 5 seconds before the spacecraft pulled away from the surface of the asteroid. The spacecraft collected more material than expected, and debris was seen coming off the collection instrument. The spacecraft will return to Earth in 2023, when the sample will land in the Utah desert for analysis by researchers. This marks the first time NASA has ever gathered a sample from an asteroid, and it will be the largest sample return mission since Apollo. A new study from Cornell University identifies more than 1,000 exoplanets where advanced civilizations would be able to find evidence for life on Earth. Each of these worlds orbits stars like our own sun and are warmed to temperatures where liquid water could pool on their surface. Advanced technologies coming online in the next few years will soon allow astronomers to detect the telltale signs of life in the atmospheres of distant worlds, possibly providing us with the first signs of life on other planets. Io, the innermost large moon of Jupiter, is the most volcanic body in the solar system other than the Earth. New observations by astronomers using the ALMA array of radio telescopes examine the ultra-thin atmosphere of Io, finding that between 30 and 50% of this tenuous layer of gas comes from these alien volcanoes. The atmosphere of Io was found to consist of a mixture of sulfur monoxide, sulfur dioxide, and potassium chloride. An exoplanet called LTT 9779b is a world which should not exist. Roughly the size of the planet Neptune, this world orbits so close to its star that its atmosphere should have blown away to space. Yet, researchers at the University of Kansas found the planet is exposed to conditions which should tear such a world apart. As technology progresses, astronomers are starting to see into the atmosphere of continually smaller exoplanets.
Looking deep into the universe, we see backwards in time, and the oldest light in the universe holds secrets to how everything around us will, one day, end. Meanwhile, stars, planets, and galaxies dance in an intricate ballet, occasionally giving birth to life. We are a fledgling species, just beginning to visit other worlds. We are a way for the universe to understand itself. The Cosmic Companion strives to bring the universe down to Earth, and we depend on your help to make it happen. For information on subscriptions and ways to donate to this program, please visit thecosmiccompanion.net. Thank you.
This week on Astronomy News with the Cosmic Companion, we talked to Dr. Meridith Joyce of Australian National University. We'll talk about her work studying one of the most famous stars in the sky, Betelgeuse. This week on Astronomy News, the Cosmic Companion, we're happy to be joined by Dr. Meridith Joyce, an astrophysicist from the Australian National University. She's recently uncovered some interesting secrets about Betelgeuse. Welcome to the show, Meridith.
Hi.
Hi. So tell us a little bit, what was your first experience with Betelgeuse dimming? Did you see it? Did you learn about it from papers and research, or did you just happen to notice it in the night sky?
Yeah, so actually the origin of my interest in this project is a bit of a funny story. Historically, I didn't look at high mass stars like this, very, very big stars. But because its brightness drop was capturing the attention of a lot of astronomers, I was approached by a colleague at the ANU who was visiting, and she asked me if I thought that I would be able to model its recent dimming behavior to understand what was going on based on a previous study of a lower mass star that I had performed. And when we got our group together to perform the modeling, we actually found that we were not able to explain the dimming event in 2019 because it was caused by an external phenomenon, which was a dust cloud. But we ended up being able to explain a lot more than we expected, including a second dimming event and re-deriving some of its sort of fundamental features like the radius and distance to the star.
And so you touched on this a little bit, but what were the fundamental differences between the first and the second dimmings?
Yeah, so it was uncovered by people that use space telescopes, so especially the Hubble telescope, that the first epic dimming event that was much greater in magnitude than the other events was caused by a dust cloud moving in front of the star. And origins of that dust cloud are speculated. It could be that Betelgeuse emitted a whole bunch of gas and dust itself. It could be that it came from somewhere else. But the kind of modeling that I do is about the intrinsic physical behavior of the star. So it's not something that could be used to deal with external phenomena like that. But in the case of the second event, where it's actually caused by the internal behavior of the star, that's something that our models did reflect in our analysis.
So what was it that caused the second dimming? What were the changes?
So this was caused by coherent oscillations in the envelope. So these are pressure waves or sound waves driven by sort of electrons, ionized particles moving back and forth in waves, as you would see on the ocean in the atmosphere and the outer envelope of Betelgeuse.
So different waves are interfering with each other. So is it sort of a destructive interference like you might see near a pier in the water?
So the nature of the wave pattern was pretty regular. So we call this a fundamental pressure mode variation, and it's actually something that we expect most stars to undergo when they have these large convection zones.
It's interesting. So you think that other stars then may be going through similar processes, and how do we go about finding those?
Yeah, so the whole the whole science of astroseismology, which is this observational technique, measures the variations, the pulsations of the star according to brightness variations. So this would be drops in the magnitude, similar to what we saw with Betelgeuse, or with radial velocity measurements, which you can get different parts of a star red shifting or blue shifting, so moving towards you or away from you, which tells you that the star is expanding and contracting in radius in some sense. And so there are there are two observational methods for inferring whether a star is pulsating in this way. And what we were able to use was the theoretical counterpart to this, which is actually a mathematical model that allows us to compute synthetic versions of this frequency variation. And it's those calculations that we then compare to the observations for any kind of star.
And so is that how you determined that Betelgeuse was smaller and closer than we believed? Or how did that determination come about?
Yeah, so these pressure modes, these pulsation modes, actually ended up being the highly constraining factor. So this was a technique that had not been applied to Betelgeuse before because it's very difficult to do for red supergiants. And when we ran these calculations, we were able to actually reproduce this fundamental pressure mode theoretically and match that perfectly to observations of the star, which suggested what the physical driving for the pulsations is. And requiring agreement with the pulsations is what gives us a very tight constraint on the radius of the star, because these astroseismic measurements are very sensitive to radius.
So it's incredible that you would have that sort of sensitivity that could measure, movements on a distant star more than 500 light years away. What sort of tools do you use to measure those sorts of things?
So historically, what would be used to infer the radius of a star like Betelgeuse, because it's so huge and it's so bright and it takes up such a large portion of our sky, is something called interferometry. And this is a way, a kind of observational instrument that's used to deduce the radius of stars. But in our case, we actually did this completely theoretically.
So is it possible that other stars are closer and theoretically smaller than we are currently measuring, or is Betelgeuse a special case?
Well, if we're, you don't want to assume that you know everything that every group has ever done, but if we're correct in our assertion that no one has ever applied astroseismology to red supergiants like this before, then it certainly opens a large number of opportunities to do similar analysis for other stars that are in the same evolutionary class as Betelgeuse. So applying this to other, what we would call variable supergiants. And certainly, to my knowledge, this technique has not been applied to other stars, so that's something that we would be interested in doing.
It's fabulous. And you also found that, Betelgeuse was not likely to explode as a supernova in the next Thursday.
No, indeed.
Can you tell us how you know that?
Yeah, so this is an interesting question. The sort of the mass, the distance, the radius to a star, in astrophysics we call these the fundamental parameters, and all of the fundamental parameters are interconnected in modeling, because you have to make assumptions about how the star behaves and the relationships between those parameters. So it turns out when you find a very tightly constrained radius, this tells you a lot about the evolutionary phase of the star as well. So because we only know it's so big, it's of X size, then we know that it can't be as far evolved as some larger star. Because the bigger a star is, the more quickly it evolves. So this star being smaller than previously thought suggests that it's earlier in its evolution, which means that it's burning helium in its core, as opposed to burning a heavier element. And it needs to exhaust all of this helium fuel first before it can exhaust all of the other elements up before it goes into a supernova. And this means that we've revised sort of the timescale for that explosion for almost an order of magnitude. So previous estimates suggested about 10,000 years. Our models, based on nuclear burning, suggest about 100,000 years.
Wow. And so how can you tell how much helium is left? How can you tell how much Betelgeuse still has in the gas tank?
Yeah, so there's no direct way to know this, of course. So this is all based on the models that we devise. But what we try to do as theorists or as computational analysis is run as many possible models of Betelgeuse as we can, and then see which of those models are consistent with as many observations as possible. And so in our case, just from a purely statistical basis with a large number of models, our results suggest that Betelgeuse's parameters are much more likely to be consistent with this early burning stage as opposed to a late one.
Wow. And so how long would that helium fusing stage last for a star the size of Betelgeuse?
I don't know an exact number off the top of my head, but between 1,000 and 10,000 years. So to exhaust that phase before going into the others. So there's an exponential decrease in time as you go up in nuclear fuel. So hydrogen burning lasts an order of magnitude longer than helium burning, which lasts an order of magnitude longer than carbon burning, etc., until you get to the supernova. Right beforehand, you're burning iron for a few seconds. So it's an exponential decrease.
Wow, that is incredible. And so what other future studies could we undertake looking at Betelgeuse to learn more about what's going on with that star?
So yeah, like I said before, with other super bright stars, super giant stars, it would be interesting to analyze them in an astroseismic and a theoretically astroseismic way, as has not often been done before. And largely this is due to the fact that the tools for doing theoretical astroseismology have only existed for the last 10 years. So the observational measurements of stars' variabilities in brightness have been taking place for 400 years, from semi-ancient civilizations to 100 years ago with amateur astronomers, but now we have the computational tools to make the theoretical complements. So pretty much any supergiant star, I think, could be amenable to some similar analysis.
Yeah, and would you be looking specifically at one band of wavelengths, let's say radio astronomy or infrared, or would there be benefit from more of a multi-messenger approach, looking at a lot of different wavelengths and bands?
Yeah, that's a good question, and one better suited to an observer probably, but certainly astroseismology is largely an optical science.
Mm-hmm. Super. Go ahead. What were you doing? Yeah. So what's next on your agenda? Are you going to continue to study Betelgeuse, or are you looking at other targets?
Yeah, so there's this instrument, this transiting exoplanet satellite survey, the TESS space telescope, and so that is currently providing us with all kinds of new data for a large range of stars. And so I like to work with observers who mine that data and find candidates that might be interesting for modeling. So I'm certainly open to any star that's sent my way. As far as the future of Betelgeuse, we only looked at what we call the linear pulsations or the linear oscillations. So moving into a nonlinear regime would be a difficult next step, but it would be a potentially exciting next step if we can get those models to work. They're quite a bit harder to use.
Right. That is super. Well, thank you so much. It was wonderful having you on the show.
Thanks for having me.
All right, and that was Dr. Meridith Joyce from Australian National University. Next week on Astronomy News with the Cosmic Companion, we're going to talk with Dr. Oscar Ellick from the University of California, Santa Cruz, about his work understanding the cosmic web, the largest structures in the universe, through computer modeling and humble slime mold. Join us each week on Astronomy News with the Cosmic Companion as we bring space and astronomy news together with groundbreaking scientists directly to listeners and viewers around the globe. We depend on support from viewers like you. To help support this program with a one-time donation or a paid subscription starting at just 99 cents a month, please visit thecosmiccompanion.net/support. If you live in the United States and you have not already done so, please remember to vote by November 3rd. Please stay safe, stay healthy, and keep your wonder alive. If you enjoyed this episode of Astronomy News with the Cosmic Companion, please download and share the episode on YouTube, Facebook video, or on any major podcast provider. For more details on space and astronomy news, please visit thecosmiccompanion.com or thecosmiccompanion.net.